Okay, let's start. So, good afternoon, everybody. So, I actually explained everything here in chapter 4 except encoders. That's why I'm gonna explain it today. So, yeah. Okay. So, as I explained before, decoder. Okay. So, you know, in the case of decoder, if I have n bits, okay, input, for example, 2, for example, if it is 2 or whatever n, the output here has to be less than or equal to the power of n. Okay. It is equal if you are going to use all the numbers. Okay. It is less if you are not going to use all the numbers. For example, it may happen that I have here 4 inputs. So in the output, I can have up to 2 to the power of 4, which is 16, which is from number 0 until number 15. Okay. But I'm not going to use the whole range. For example, I'm going to use until 9, from 0 to 9. You got what I'm saying? So that's why I'm saying less than or equal. But most of the time it's equal. But in general, it can be less than or equal. Okay. The way it works, as I said before, it was very simple. So all what you have to do here, for example, if you have two inputs here, in case if you have 2 inputs, you should have 4 outputs here. This output, I'm going to say output number 0, number 1, number 2, number 3. Very simple. If the number here is number 3, which is 1, 1. So actually, this output is 1, and all other outputs are zeros. Is that okay? So very simple. So it's a logic circuit. This logic circuit should only one output is 1 to tell you what is the input. If the input is 2, number 2, so number 2 is 1, the other outputs are zeros. Is that okay? So this is decoder. Okay. And now I'm gonna talk about encoder. Okay. So decoder, encoder. So encoder is actually the opposite. So here the opposite means this will be inputs. So here, if I have so here, if you have, for example, n outputs, so the input here has to be less than or equal to the power n. It's going to be the opposite. Okay, it's the same thing. If everything is the same, but it's going to be the opposite. For example, here you have bin number 0, bin number 1, bin number 2, bin number 3. Okay, it should be only one input here, 1. The other one should be zeros. So only one input is 1. The other ones are zeros. For example, if this one here is 1, and I have zeros everywhere, so actually the output here should be number 2, which is 0, 1, or 1, 0. Okay. So number 2. So if number 2 is 1, so the output is going to be number 2 in binary. Is that okay? Same thing if it is, for example, if the 1 is here, so the output should be number 3. So actually it's the same thing like what I did here, but it's going to be the opposite. Is that okay? So only one input here is 1. The other ones are zeros. Okay. But be careful here, because this is active high. I can make another version, as I explained before, can be active low. Okay. So this is active high. In case of active low, this is exactly same thing here as well. In case of active low, so I'm going to put bubbles here, as you know. And in this case, only one input should be 0, and all the output, all the other ones should be 1s. You got what I'm saying? So if you select, if it is active low, and you want to select number 0, so it has to be 0, and the other input should be 1s. If you select number 3, so 0 is here, the other one should be 1s. Is that okay? If it is active low. Anyway, so now I'm gonna discuss how can we design this encoder. Okay. I want to tell you something important, guys, here. The purpose of this course is not to show you how can you design a complete digital system. Okay. As I said in the very beginning of this course, the purpose of this course to learn component that you are going to use later to make digital circuit like a computer. So now maybe still you didn't understand well or still it's not clear, yeah, you have encoder, I know how it works, you have multiplexer, I know how it works, but how are gonna put everything and today, or in chapter 6, I'm gonna talk about counters, I'm gonna talk about registers, okay, but how can you put, and already I explained how can you make multiplier, how can you make comparators, all of these components are used to build a digital system like a computer. You got what I'm saying? This will be, so in the future, when you take future courses, so the instructor is not gonna teach again what is encoder, what is multiplexer. You got what I'm saying? Just they are gonna use them to build a digital system. Is that okay? So anyway, so yeah, that's exactly what I explained here. So let's see how can we design this encoder. So for example, as you see here, I'm gonna start if we have 4 to 2 encoder. So we have 4 inputs, we have 2 outputs here, okay? And this is active high. So let's look at the truth table here. So as you see here, this is the input here. So if y0 is 1, so everyone else should be zeros, okay? And the output here has to be number 0 in binary, okay? The other possibility is when y1 is 1, so everyone else should be 0, okay? And the output here has to be number 1 in binary. Here, this is the 1 is here, should be number 2. If the 1 is here, should be number 3. Is that okay? This is the truth table. This is how it should work. Is that okay? Now, how I can design the circuit? Very simple. I'm going to tell you how. So this is the truth table. Now I'm going to show you how I design the circuit. Okay. So again, similar to what we did before, but there is a small difference here. A small interesting difference. Look here. What did we do before? I'm going to tell you. So what we did before, for example, here, I want to design A1. So I'm going to find some ones here, 1 and 1 here, and then I'm going to take the min term here, and then take the min term here, and OR. I make it OR. That's what we did before, right? You need to take the min term here and min term here and use OR. Same thing here for E0. You have to take this one, get the min term here, and then use OR. Okay, but I'm not gonna do. I'm gonna do it differently in this specific case. I'm gonna tell you why this is specific case, why it's different. Look how I'm gonna do it. Look here. When I design A1, okay, here, look here. So again, I'm gonna look at these 2 cases. Okay, but in this case, I'm gonna say here Y2 or Y3. So here I'm gonna say E0 is actually Y2 or Y3. Yeah, sorry, this is E1. So E1 here, as you see, E0 is here. This is E1. So Y2 or Y3. That means, what that means, A1 should be 1 when Y2 is 1 or Y3 is 1. If any one of them is 1, A1 should be 1. Is that okay? But wait a second. This is not a midterm. Usually, if it is a midterm, it has to be Y3 prime, Y2, and then Y1 prime, and then Y0 prime. This is to make it midterm. I'm right? Anyway, you can make it this way and do simplification. You will get this one. However, listen to me. In this specific case, I'm not going to use the midterms this way as we did before. Why? I'm going to tell you why. Because there is only one case where Y0 is 1. Okay? This is not going to happen again. This is different from what we did before. What we did before, if you have, for example, here, yeah. I want to, hopefully you understand this part, otherwise you will be confused. What we did before, if you have, for example, X, Y, Z, and then you have here 0, 4 zeros, 4 ones, okay? And then 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, and then you need to find the midterm here, midterm here, midterm here. Okay. So what I'm saying is that here, this one can be 1 here, also it can be 1 here, or this one can be 1 here. Okay. That is why to get this specific case, it has to be Z and Y and X prime to get this specific case. However, our case is different now. Our case is I have XYZ, which is actually Y0, Y1, Y2, whatever you call it, but only one of them is 1 and other ones are zeros. Okay? Because of that, all what I can say, in order to get this specific case here, I don't need to say x, y prime, z prime. In this specific case, I can just say x. So when x is equal to 1, I'm here. So I don't need to mention everything. I think if you write everything and you simplify, you will get the same result. But I just want to remove any confusion here. It's just a very specific, very special case. This is not what usually we do, okay, because this is just a very specific case. So here what I'm saying, A1 here, A1 has to be 1 in one of two cases, when Y2 is 1, or when Y3 is 1. That's why I made this one. Okay, same thing for E0. E0 should be 1 in one of these two cases. Okay, this case or this case. This case is actually when Y1 is 1, as we see here, or Y3 is 1, as you see here. And that's it. That's it. So I am done. So this is actually the encoder. So the encoder will it looks like something like that. It has 3 inputs. Okay. Sorry, it has also that's maybe a little bit funny. It should have four inputs, including Y0, but actually Y0, I'm not gonna use this input. So this input is not included here, and still the circuit is gonna work. Okay. So this is how the encoder looks like. Okay. So if any one of this one is 1, you are gonna get the correct output here. Any questions? Again, nothing is new. I created a truth table. From the truth table, I get the logic expressions. Nothing is new, but there is only one small difference from what we did here and what we did before. As I told you, here I'm not going to use min terms, okay? Because this is, I know this if Y0 is 1, this should not happen again. Okay, that's why it's enough to say Y0 here to refer. When I select this case, I'm going to say just Y0. When Y0 is 1, so it is this case. Okay. Okay. Can we here? I'm gonna repeat everything again, and this is something very important, guys. Listen to me. Sometimes I make other for 4 bits. Okay. In exams, I can ask you to make other for 2 bits, 5 bits, 6 bits, any other number of bits. You got what I'm saying? It should be easy because it's the same. Okay. So same thing for multiplier, for same thing for everything I explained in this course. Okay. So for example, now I'm gonna go, if I want to make a decoder 8 to 3, you'll find it's exactly the same thing. Okay, as I'm gonna show you here. So in this case, I have 8 inputs, I have 3 outputs, 8 to 3. Okay. So this is the truth table, as you see here. Okay. So as you see here, for every input I have, it's gonna be only 1. As you see here. So every input can be only 1 in one case, and then 0 everywhere, because this is how encoder works. Then as you see here, if this one is 1, so the output has to be number 0. If the 1 is here, so this one has to be number 1 in binary, number 2, number 3, number 4, number 5, 6, and 7. Is that okay? It's easy, right? This is so it's easy to create the truth table. Now, let's find the equations. Again, nothing is new. Similar to what I have just taught right now. Okay. So again, A2. If I take A2 first, A2 is actually should be 1 in these 4 cases. In these 4 specific cases. That's why I'm gonna say A2 equal. So this is Y4, Y5, Y6, Y7. That's it. So I'm gonna say, as you see here, A2 equal Y7 or Y6, Y5, Y4. That means if any one of these inputs 1, A2 should be 1. Make sense? Same thing, if I go for A1, same thing again. What I'm gonna do now, yeah, so in these 2 cases and these 2 cases, okay? So this one actually, it is at Y2, this one is at Y3, this one here, Y6 and Y7, okay? So I'm gonna, by this way, I can get A1 here, okay? Any questions? So same thing here for A0. For A0 here, this is the cases here for 1s. This one is corresponding to Y1. This one here for Y3, Y5, and then Y7, okay? And this is the ones I'm using here. Easy, right? That's it. Once you have the equation, I can draw the circuit, and this is how the circuit looks like. Maybe funny, still we don't we don't have y0 here, as I don't use it. Yes, we have y0 as input, but I'm not going to use it here. You get what I'm saying? I don't need it. Okay. Any questions? You understand what you should know now? Number one, what is encoder as a device, how it works, right? Number two, you should understand how can you make the truth table, okay? You should understand how, or you should learn how can you find the equations, okay? How can, and by this, if you have the truth table and you have the equation, that's it, you design an encoder, okay? Any questions? Okay, so now the encoder I designed right now, it has two main problems. I'm going to explain what are the problems, and then I'm going to improve it. I'm going to design it. It's like I designed a very simple encoder, okay? It has two problems. I'm going to explain what are these problems, then I'm going to explain how can you improve it, okay? So nothing is new, just I'm going to talk about how can you improve it. What are the problems? I'm going to tell you what are the problems here, okay? The first problem we have is here we assume for the input, in the input here, we assume only one input is 1 and the other ones are zeros. Is that okay? Can you guarantee that? What if I'm gonna put 2 ones here? You got what I'm saying? So the output will be unpredictable. It's gonna be wrong. You got what I'm saying? So this is the first problem. The first problem is only one input has to be 1 and all the other input should be zeros, okay? But you should do that. But what if you didn't do that, okay? For example, here, if I put here 1 here and 1 here and then put zeros everywhere, the question is, you will get some random output here, okay? For example, let's look at this specific example. So here, if I put here y6 is 1 here, y6 is 1, y7 is 1. So actually, I'm gonna get 1, 1, 1, which is number 7. Okay, this may not be a big problem, but for example, if I assume another case, if you have here, so here, for example, if you have here, if I select 3 and 6, for example, okay, for example, if I select 3 and 6, and then I put zeros everywhere, okay, look at the equations here. So here we have 6 here, 6 here, and then we have 3 here. So I'm gonna get number 7. So so even if I select 6 and 3, I'm gonna get some random output. It's not 6, it's not 3. I got 7. You got what I'm saying? So this is a problem. So to fix this problem, I'm gonna redesign the encoder to have a new concept, very interesting concept. This concept is priority. For example, so that's what you are going to see right now, okay? I'm going to assume the input that has higher number should have higher priority. So again, let me summarize what I said. Very simple. What I said, again, if one input is 1, all the other inputs are zeros, we don't have a problem, okay? However, it may happen that users are not going to follow that. So in case, for some reason, if you have here 2 inputs are 1s, okay? Based on the design of the encoder I did here, I got random number. It's not 6, it's not 3, 7. It was 7, random number. Is that okay? So what I'm gonna do is I'm gonna redesign it so that if a case like this one happens, I want the output here will be similar to the input that has higher number. So I'm gonna give them higher priority. So if I put 1 here at 6, 1 at 3, so I'm gonna get 6. You got what I'm saying? I'm gonna show you how. It's somehow interesting. So it changes the design to solve this problem this way. In general, so for example, if I put 1 here and 1 here and 0 everywhere, so I'm gonna get number 1. So always the number that the input that has higher number, I'm going to give more priority to this number. So once this one is 1, regardless of the lower inputs, I'm going to get this input. You got what I'm saying? You can do the opposite. This is a design. You can design as you want. Okay? It's up to you, but I want to design it this way. Okay? So in general, for example, again, if you have here 1 at 5 and 1 at 0. So in this case, you will see the output is 5. You understand what I'm saying? So I want to fix this problem here to do this way. So this is the first problem we have in this design. That's why I'm going to improve it. What is the second problem? You told us we have 2 problems. Yes. The second problem is, look at this one. I told you if you have here 1 and we have 0 everywhere. Okay. So I'm going to get here at the output number 0. Is that okay? Okay. What if I have 0, 0, 0, 0, 0, 0, 0? It means I don't have input. There is no input. All of them are zeros. I'm going to also get 0 here. Okay? Because if you put here 0, 0, 0, everywhere, you are going to get 0, 0, 0. So now there is a confusion. Or there are 2 cases, it's going to give you the same output. So when I get 0, 0, 0 at the output, I don't know if I get 0, 0, 0 because the input is 0, 0, 0 or because Y0 is 1. So I want to differentiate between these 2 cases. This is the second problem. Any questions? Okay. Yes. We will do something like that just in a minute. We'll do something like that. But to solve this problem, what I'm going to do is I'm going to introduce another output here. I'm going to do another output. This output should give me 0 or 1. If you give me 0, that means there is no valid input. The word valid input means there should be at least 1 here. Okay. If you give me, or the other way. So here I'm going to introduce 1 output. This output should tell me if all the inputs are zeros or not. You got what I'm saying? So I'm going to introduce another input to tell me if there is an input, okay, at least there is 1 input with 1 or all of them are zeros to solve this problem. So now I'm going to show you now, guys. So again, what I did, I designed very simple encoder. I told you this encoder has 2 problems, you remember, okay? And then I'm going to show you how I'm going to redesign it again to consider these 2 problems, okay? So let me show you. Yeah, look how I'm going to design it. So here, as I told you, number 1, I'm going to introduce a new output here. I'm going to call it V. This new output should tell me if the input is valid or not, okay? So here, I'm going to have, this is a new truth table. I'm going to say if the input is 0, 0, 0, 0, okay? So regardless, so now the output here has to, this one should be 0. In any other case, this one should be 1 here. You got what I'm saying? So that means this output should tell me if the input is 0, 0, 0 or anything else. You got it? That is why when the input, in this case, when the input at 0, okay, or in these 2 cases, I'm going to get the same output, which is 0, 0, 0. Here in this case, it's only 2, so I'm going to get 0, 0, okay? In these 2 cases. However, to differentiate between this case and this case, I'm going to look at this one. This one is going to tell me this output. Is that okay? This is number 1. Number 2, look at this is really interesting part, as I told you. Look at the second part here. Okay, so now I was able to fix the first problem. The second problem. So the second problem now, I can differentiate between if the input is 0, 0, 0 or a valid input. This is the first part. The second part, look at the second part. Look what I'm going to do. Look, you know what I'm doing here, guys? I'm just changing this truth table. I'm making the truth table in a different way to solve the 2 problems I have. Okay, so let's see this truth table. Okay, so look here. Look what I'm going to do. I'm going to say if input number 3 is 1, regardless whatever you have here, I need to see number 3. That means if you have here 1, regardless, I don't care about anything else. So if you put here 1 and here 1 or here 1 or here 1, I don't care. Okay, so that's why this one has the highest priority. Now I can solve the second problem, or sorry, the first problem. Okay, now if you have more than 2 inputs or 1s, the one that has higher number, that's what you are going to see at the output. You understand? Look how I made it in the truth table. Very important. The way I made it, if this one is 1, regardless of what I have here, okay, the output should be 1, 1. That means this can be 0 or 1, it doesn't matter. 0 or 1 doesn't matter. 0 or 1 doesn't matter, because this one has higher priority. You can redesign it again. That's the design. It's like when you write a program, I write a program in different ways, right? You can redesign again so that you can give priority to the 0. Okay, so if you have 0 and 7, so the output will be 0. You can make it this way if you want. Okay, so let's see the next one here. Again, here, if D2 is 1, and D3 has to be 0, okay? And then whatever I have here, I don't take care. That case, in this case, I'm gonna output 2, number 2. You got what I'm saying? So because this one has higher priorities than this one. So once this one is 1, but this one must be 0. Otherwise, there will be contradiction with the next one here. Okay. So if this one is 1, this one is 0, I don't care about the lower priority inputs. Okay, please. So I'm gonna output number 2. Same thing here. If number 1 here is 1, okay, and these ones are zeros, regardless what I have here, I don't care. So if you have here 1 or 0, I don't care, whatever I have here. So in this case, you have to output 1. Is that okay? You understand the idea here of making a priority if you have 2 inputs or 1s. So I'm going to select the one that has higher number, and that's what you will see the output. You got what I'm saying? Is that okay? Now, given this truth table, how can we get the function? I'm going to tell you how. Very interesting thing as well. Look here. This is how the truth table completely should look like, right? I have 4 inputs here. These are the 4 inputs I have. I have 4 inputs. That means I have 16 cases. 16 cases, okay? So, and I have 3 outputs, X and Y and V. Is that okay? Look at this. This one here is going to be only one case, which this case here, only one case here, okay? This one here is going to be only one row here, which is, this row, only one row here, okay? So I just, 0, 0, 0, then it has to be here, X, 0. That's what I did here. This one is only one case. What about this one? This one actually 2 cases. One time when X is 0, one time when X is 1. You got what I'm saying? That's why what I did here, look at the color. So I take this one here, and I take this one here, which is actually I'm saying if X is 0, okay, this case, I'm gonna get this output. Same thing, if X is 1, I'm gonna get the same output here. You got it? It's like a mid expansion. This is like a compact. Okay. What about this one? This one here. This is actually 4 cases. Okay. So that means 4 cases. It means if the input here 0, 0, or 1, 0, or 1, 0, or 1, 0, in any of these cases, given these fixed cases, I have to see this output. That's why you can see this one contributing by 4 cases here. Look at the table here. So this one actually is here. It is also here. It is also here. It is also here. Why? This is, don't care here, 0, 0, or it is number 1, or number 2, or number 3. So whatever you have here, I'm gonna get the same output here. Okay. What about the last one here? Again, it's the same thing. This one is gonna become 8 cases. 8 cases. 0, 0, 0, and so on. So as you see here, so this one here, this one actually is going to be shown here, and here, and here, and here, 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 here. So in these 8 cases, I should get the same output. Okay, it's the same output. Why 8 cases? As you see here, this is number 0, because I don't care about these 4. So this is number 1, number 2, number 3, 4, 5, 6, and 7. Okay. So if any of these cases happen, I should get them. Okay. Again, once you have this complete truth table, it's very easy to calculate this function and this function and this function. It's very easy to calculate them. Okay, and that's what I did. So I can do simplification this way. I can do simplification, and then after that, this is the circuit I got at the end. So in this circuit here, in this circuit, I was able to solve the two problems we have. Okay, so to make it simple, in this circuit, as you see, we have here one output, one extra output. This one should give me 0 or 1. If it gives me 0, it means all the inputs are zeros. It gives me 1, that means I have a valid input. Valid input means at least one input is 1. Okay. Same thing. Also, I was able to solve the problem when you have more than one. For example, if you have this one is 1 and 1, so I can see number 3 here. If I have here 1 and 1, I can see number 2 here. Okay. Any questions? Okay. So here I did this one for in case of 4 and 2. You can do the same thing. It's exactly same thing for 8 and 4, but maybe it's going to be more complicated, but you can expand it to 8 and 4. It's exactly same thing as I have just explained right now. Okay. So if I have all the inputs are zeros, so now in this case, I have 8 inputs. I have, this is the normal 3 output, and I have 1 extra output here. As same thing. So here, in this specific case, I'm going to have 0 here. Everywhere I'm going to have 1s. This is the same thing as V, okay? But just I made it bigger. Also the same thing here, guys. If this one is 1, regardless whatever you have here, I have to get number 7. If this one is 1 and this one is 0, so regardless of what you have here, I should get number 6 and so on. Okay? Anyway, you can continue the same way. Maybe it's going to be more complicated here to do it, but you can use the same concept. The last thing here I have in the encoder to teach is, I just want to show you one example for a practical priority encoder, a chip with a priority encoder, as you see here. Maybe you don't have in your kit, I'm not sure, but I don't remember actually, but just to show it to you. So we have 8 input priority encoder. Okay, this is the number 148. Let's see, but you see bubbles. So when you see bubbles, what it means? It means it's active flow. Active flow. That means normally all of them are ones. Only one input should be 0. One input is 0, and everyone else should be ones. Is that okay? So I just want to show you how the truth table works here. So actually here we have an enable, one enable here. This is the enable, okay? And because it has bubble, so if you put 0 here, you actually enable it. If you put 1, you disable it. So you can see here in the first record you have here, okay? Here the enable is 1. So that means you disable. It is disabled. It's not working. So that's why regardless whatever you have here, I'm going to have just 1 at the output here. 1s here like zeros, like zeros on the other ones, because this active flow. 1 1 1 1 like 0 0 0 before. Anyway, active flow. Anyway, so now it is disabled, so it's not going to work. Now, okay, now if it works, so I can have up to 8 cases, and that's exactly what happens here. So here we have 8 cases, it works. And then in these 8 cases, as I have just explained right now, if input number 7 is 0, and all the, regardless of what you have here, and this one is 0, the output has to be actually 0 0 0, which is actually the opposite, because everything is inverted. Okay, so because this is number this one is number 0, so I have to see 1 1 1. Okay, but actually because it's inverted, I'm gonna see 0 0 0. You got what I'm saying? Everything is inverted. So here, yeah, so I'm gonna see 0 0 0. Okay. Now, as I told you before, we need one extra output to tell me if the input is valid or not. Actually, this extra output is here. Okay. But they actually give you 2. Okay. One and the invert of this one. So you can see here. Okay. So one of them and the invert of this one. So you can see here Yeah, so you can see here they are the same, but they're just inverted. So this one can tell you if the input is valid or not. Okay, so everything else is the same. For example, if the 0 is here, so actually this is numbers. This is the invalid case. This is not in, yeah, this is a case when all the inputs are 0 0 0. Here it's all the input 1 1 1 1. Okay, so you didn't select any input when it is 1 1 1. So in this case, I can, these two inputs is gonna help me. Okay, so one of them is active high, the other one is active low, or one of them is the opposite of this one. So if this one is 0, that means you have a valid input. If these ones are ones, that means you have a valid input. Okay, that's why it's gonna be 0 or 1 when you don't have a valid input, when all of them are ones. If you didn't select any input, you got what I'm saying? Other than that, if you look at the other cases here, for example, in this case, I selected number 5. Okay, so regardless of what you have here, you have to see number 5, but inverted. So this is actually number 5 is actually 101. Okay, this is number 5, but it's going to be inverted. That's why you can see 0 1 0 anyway, because it's active low. Any questions? So again, we should understand what is encoder, how we designed it. You should understand what the problems, two problems I have, and priority encoder. Okay, so that when you have a chip like this chip, you understand what is priority encoder. Okay, any questions? Okay, I think I'm done with this chapter. What I'm gonna do now, I'm gonna move to last chapter, chapter 6. Okay, chapter 6 is very, very easy chapter. So in this chapter, and already several things here I already taught before, and it's very, very easy chapter. So in this chapter, I'm gonna teach number 1, very important component in any digital system. We have something we call register, shift register, counters, two different types of counters. Okay, so these are basic component of any digital system. So let's start with the first one, register. What do you mean by register? I'm going to tell you. Okay, remember when I explained the flip-flop, what did I tell you when I explained the flip-flop? I told you flip-flop is a storage unit that can store only 1 bit. Okay, it can store only 1 bit. However, in any digital system, usually numbers are greater than 1 bit. If I get number from the memory, this number can be 8 bits, 16 bits, something like that. If I get number from the user, okay, this number usually it's more than 1 bit. Okay, so now the question is that how can I need a storage space that can store information that's greater than 1 bit. You know what I'm saying? And that's what we call a register. Okay, so a register is actually, as you will see right now, inside the register, it has a number of flip-flops. Okay, and a register, it's exactly similar to a flip-flop, but the difference is that a flip-flop can store only 1 bit. Often it's going to store data, and the size of this data is only 1 bit. What if my data is 8 bits? Again, as you will understand in the common courses, when I say 8-bit data, that means you have a sequence of 8 bits. 1 2 3 4 1 2 3 4. Okay, so this is one piece of information. I can't cut it. You got what I'm saying? It's just one piece of information. I cannot cut it. It doesn't have any meaning to cut it. You got what I'm saying? This can be a temperature, it can be speed, it can be voltage, whatever you are, pressure, whatever you are measuring. Something you measured and you are represented in 8 bits. So they are together. It's one unit, one piece. You should understand that, okay? It doesn't have any meaning to cut it. You understand what I'm saying? It's a number, one number. So this one number, I want to store it in a storage so that I can use it inside the digital system, okay? So that's why you have what we call a register here. So the main difference between flip-flop and the register, flip-flop can store only 1 bit. Register can store, both of them are storing data for sure. So this is stored data and this is storing data. But here the size of the data is just 1 bit. Here the size of the data is n bits. And I can design this n bits. I can design it. If you want to make it 4 bits, you can make it. If you want to make 16, you can make 8, 7, 8, whatever, you can make it. You got what I'm saying? So it's a storage space. I can store the result in this space. Okay. So actually, the way you are going to do it, n bit register consists of a group of n flip-flops capable of storing n-bit binary data okay? Actually, as you will see in the future, in any digital system, we need to use registers a lot. Why? I'm going to tell you why. Look here, for example, you remember the 4-bit adder I explained in chapter 4, okay? So now I want to add 2 numbers, and then I want to store the result somewhere. So usually what happens is, listen to me, just to understand the main idea here. To create a complete system, usually what happens is that I need a storage here for number of bits, register A. I need another register, for example, register B. And these registers are connected, hardware connected to the other. And then the output of the other is going to have to be stored somewhere in another storage unit, okay? What usually happens is, listen to me. For example, I want to add a number given me from the user, plus a number in memory, okay? That's, I want to, okay? So usually what happens, I have a memory, I'm going to get a number from the memory. I have first to store the number here. Number 2, I'm going to ask the user, please, user, give me a number. The user give me a number 10, 11, whatever. I'm going to put the second number here. You get what I'm saying? And then I'm going to do addition. Once you do addition, I have to store the result somewhere. After that, I can take the result here. I can display it on the screen, or I can store it in memory, for example. I'm just trying. That's what you will see in 3130. I used to teach 3130 for many years. So that's what you will see in 3130. In 3130 or in computer architecture, you will see what I'm explaining here. We need registers to store data. So here, this is more like a small system. This is a small system. So here we have a register that is storing, for example, 4 bits. This one is going to connect it to the other. We have another one that's going to store 4 bits. This one is connected to the other. The result is going to be stored in 4 bits, okay? And then when you have a complete system, before I do the addition, I have to bring the numbers first. I have to bring the 2 numbers the 2 numbers I want to add, I have to bring them first. Put one here and put one here. What do you mean by bring? Usually, I'm going to bring them either from memory. Okay? So for example, I want to store 2 numbers from memory, okay? Or I'm going to bring them from the user. I'm going to get some number from the user, put the numbers here, and this one connected to the other. The result, the other will come here. Once it comes, once I get the result, I store it somewhere. After that, you can do whatever you want to do, okay? You store it in memory, you can display it. I can compare the result with a certain number, so the output here can go to the comparator. I know it may be a little bit hard. I want you to get some idea about it. Yes, the purpose of this course is teaching just separate pieces, but I just want to give you some idea about how in a real system, we're going to connect these 2 pieces together to create a system, okay? Digital system, okay? I'm doing my best on this one. But anyway, but regardless, to do that, you need registers. You got what I'm saying? To store data in these ones. And these registers are connected. It can be connected to other, it can be connected to comparator, and so on. Okay. So now, what I'm going to explain now, how can I create? I'm going to repeat it again because it's maybe a little confusing to students. Please, guys, listen to me. What I'm saying, if I have a data 4-bit data, what it means? It means it's just one piece of information, one number. I can't cut it. I can't separate it. Just one piece. So I have to store this piece or I have to read this piece. I can't separate it. So this number can be like a voltage. You measured the voltage, you measured the temperature, you measure something, and then you convert it to binary, and then it became one piece of information. Okay. Even 1 bit can be also one piece of information. Okay. So think this way. So if I want to store this number, if I have to store the whole number in a register, if I want to read, I have to read the whole number of registers. They are not separate bits, please. Yes, I'm going to store them as separate bits, but I'm gonna use them as one unit. Okay, so I'm gonna store the whole number or read the whole number. Okay, anyway, so let's see how we'll do it. Very simple. So here I'm gonna show you how we can create very simple 4-bit register. Look how I made it here. First of all, I'm gonna use 4 flip-flops. 4 flip-flops here. All of them reset is connected together. Reset, so that this is just for initialization. If I want to initialize this register, I can simply put 0 here. Once you put 0 here, okay, so all of them are gonna, you can clear the register. You have a storage unit, okay, so you can clear it. So I can store this one. I can store zeros in this register. Okay. One more thing, guys, you can see. Also, this is something you are gonna learn in 3130. You remember when you made variable in C language? You remember variable in C language when you said y equal y plus 1, y equal x plus whatever 2, some variable like this one. These variables actually in physically they can be either memory location or registers, and that's what you are going to do in 3130. You get what I'm saying? So you can think about this one like a variable. So I can, is this, for example, if I want to make like x equal to 0, physically I can just put 0 here. I can clear all of them. Okay, so you can think this way. So this value, this is like one variable I need to write or read. I want to read the value there or write or clear it. Okay. Anyway, so let's see how it is, how it works. It's just very simple, very simple. Here I'm using this one is 4 bits. So I'm going to use one flip-flop to store every bit, as you see here. So this one is going to store the least significant bit. This one is going to store the most significant bit. This one is going to store the next, sorry, this is bit 0, bit 1, bit 2, and bit 3. This is the most significant bit. This is the least significant bit. Is that okay? Again, I'm not going to read individual bits. So it doesn't have any meaning to read this bit. I want to read the 4 or write the 4 because the 4 is one unit, one piece. You got what I'm saying? So anyway, so the way it works is that the number is stored in the register. You can get it from here. This is the number you have in the register. Okay. So I have 4 bits. Every bit is stored in one flip-flop. Okay. And then all of them have the same clock, as you see here. And again, if I want to clear it, I can just put 0 here to clear it. Okay. What if I want to store a new value? Like, for example, when I say x equal to 7 in C language, how I can do something like that here? So I want to store number 7 here. How I can do it? Very simple. So that's why I have inputs here. So I can put here, this is the input value I have here. So I can put here number 7. Number 7 is actually, I guess, 0, 1, 1, 1. I can put number 7. And then when the clock comes, the input here will be stored here. So you can store number 7. You got it? So again, you can see here, it's like you have, this is the input. And this is the value stored by the flip-flops. So once I put a number here, at the first clock, this number is going to be stored here. You got it? So now in exams, anything, is it difficult if I tell you draw a register with 3 bits, 3-bit register or 5-bit register? It will be the same thing, but you are going to just add one component. That's it. So if it is only 2 bits, so I'm going to cut here. This should be 2-bit register. You got what I'm saying? Again, there is no way to just read one flip-flop. No, they are together. Read everything or write to everything. Okay. You got it? Any questions? So you can see it like this is the register. This register has input number. I'm going to call it I, and the number is stored in the register. I'm going to call it A. And then it has one bit here for when you put 0, you clear. So now A is equal 0 once you do that. Also, you have a clock. You have a clock here. So once you have input here, this input is not going to be shown on the output until the clock comes, rising or falling. Okay, based on how we use it. This one is rising for sure. Any question? Okay, so this register has a limitation. Then I'm going to improve it. Very simple. I'm going to show you how. What is the limitation here? Listen to me, because this is also interesting concept. What is the limitation here? The limitation is once I put the input here, at the first clock, the input will be stored at the first clock. Okay. In digital systems, usually I don't like to make it this way. Why? If you think about a big system, in a big system, number one, usually all components are connected to the clock. So all of us are connected to the same clock. Okay. However, I should have the capability to do any operation at a certain time. You got what I'm saying? Unrelated to the clock. Okay, that's why usually we have something like enable. You got what I'm saying? So what I'm gonna do right now here, I don't have capability. Once you put the input here, at the first clock, it's gonna be stored. I wanna have, because sometimes, guys, in a digital system, there should be a sequence of events. So maybe I have input here, but I don't want the input to come to here at this moment, at the first clock. Okay, for some reason. For example, I'm going to use this number in addition first. So I should have the capability to do that. So all what I'm going to do, something like an enable. So now, this is the register. Even if you have an again, all what I'm gonna do, this is the same register. I have here input I have output A, okay, and still you have a clock, okay. On top of that, I want to add something here like an enable, whatever active flow, it doesn't matter, enable, okay, something like that, okay. So that when the enable is 0, if it is not enabled, okay, so this output is not gonna be shown here at any clock. It's not gonna be shown. You get what I'm saying? I want this output to be stored when this enable is 1. You understand? Again, this gives me the flexibility to control, because if you think about a big system, there are a sequence of actions. I have to do addition first. After I do addition, now I have to upload, or I have to load the register with this value. Okay, so regardless of the clock. So that's why, to make it simple, I'm gonna add here something like an enable. Okay. So at the time you want to upload this input, I'm going to make the enable 1. Once I make the enable 1, okay, at the first clock is going to be loaded. Still the clock is important, okay? But I don't want to use the clock as an enable. So it's going to be 2 separate things, okay? Still you need a clock to enable it. But you need so that's why I'm gonna this is a very basic register. I'm going to improve it to make it this way. So if you see, it looks so complicated. No, it is not. I'm going to tell you why. So what I did here, guys, look, I just added a new input here. I call it load. Okay, load. Load here like enable, exactly like enable. Okay, so if load is 0, no change. So regardless of, so the input you are going to have here is not going to be stored. No change. Okay. However, if load is 1, so that means I'm loading the register with the new value. At the first clock, still clock is important. Okay. So now I have control on the timing. I have control when this loading should happen. You got what I'm saying? So anyway, so all what I did is after I introduce this input, I call it load. All what I did, I just added, look here, I added this circuit here, this same circuit here, the same circuit here. But wait a second, it looks complicated. No, it is not. You know what this circuit is? I'm gonna convince you now. You know what this circuit is? This is simply a multiplexer. So I took it alone here to explain what. So this circuit is actually a 2-bit 2 to 1 multiplexer, and the load is gonna control if the input here is gonna come from here or here. The input here, I mean, if you look here, the value I put here on G, because this is the value is gonna be stored here. You got what I'm saying? Look at the idea. Idea is very simple. If load is 0, This is a multiplexer, and then I'm gonna get A1. I'm gonna put A1 here because of the multiplexer. The multiplexer will do that. So that's why there is no change. When the clock comes, no change. I'm gonna have to store the same value, no change. Okay. Or when load is 1, the multiplexer is gonna put I1 here. So this is the main thing. So at the output here, I'm gonna put either AI or II. A1, A or I. When load is 0, no change. So I'm gonna put this value back again here, so that no change. Or I'm gonna put I to load the register. So if you think, yeah, that's what I'm explaining here. So this circuit, it looks a complicated circuit. No, it's not. And the same circuit, I just repeat it. So if you see here, just here what I did here, it's the same circuit repeated. Okay. This circuit actually is multiplexers. Look how this one looks like. Okay. So the way it works, you know, in case of multiplexer or decoder, we have here and then we have OR. Okay. Look how it works. The way we do it here, in one input I'm gonna put AI. In one input I'm gonna put II. Because I'm going to select between these two, either A or I. In case of no change, I'm going to select A. In case of load, I'm going to change this one. Okay. And then I'm going to put here load. And I'm going to put here load prime. So that when load is 1, I'm going to get here AI to input of the flip-flop. When load is 0, so AI is going to come here because this one will be off. So this one is going to come here. So again, it looks complicated, but it's not. It's a multiplexer, very simple. And that's exactly what I'm explaining here. So what I'm explaining here, if load is 0, okay, so I'm going to put here 1. 1 is here. AI is here. Okay, so that's why I'm going to get here AI. Okay, and here is actually load prime. So load is going to come here. And load prime is going to come here. Okay, but he put 2 inverter and something like that. Anyway, so that's why I'm going to, here in case of load is 0, I'm going to get here AI so that I make no change. The second case here, when load is 1, you can see here. So I'm going to put here the inversion of load and the load here. And here, because here we have 0, I'm going to get here 0. This is II, so I'm going to get here II input. So now, and this is the input of the flip-flop. So we have a flip-flop here. Okay. So the input, in case of load is equal to 0, no change. So I'm going to input the same value again. Or I'm going to input the new input when you load it. Okay. Again, guys, what I did here is just very simple. What I did, number 1, make it simple. What I explained here, guys, number 1, you should understand what's the meaning of register. Okay, it's a storage unit to store a number of multiple bits. Okay, what this means, it means if you want to store, I have to store the whole number, 8 bits, 16 bits, whatever the size of the number. Okay, when I read, I have to read the whole number together. It doesn't make sense to read individual bits. It doesn't make any sense because this is the whole number together. If it's a temperature, so I need it's one piece of information. I store it to everything or get everything. Okay, this is what you should understand. Number 2, you can see how I created registers using a number of flip-flops. Okay, you can see the flip-flop as a register that can store 1 bit. Yes, you can see this way. Okay, also we don't say this way, but yes. Okay, but anyway, so here also I told you the problem here. This one does not have an enable. Okay, to have a control. So now that's why I modified it this way by adding something like a multiplexer here. Okay, to select between either you put here AI, E0 or I0, E1 or I1. Only you select based on the extra input I have here. Okay, this is very important concept to understand, guys. Please, in any digital system, I should have a sequence of events. You got what I'm saying? So this load should happen at certain time. After I finish multiplication, after I finish addition, there should be a sequence of events, right? That's why I should have a control when this load should happen. You got what I'm saying? For example, this input can come from multiplier. This input can come from other. So I have to make sure I have to finish the addition first. I have to finish the multiplication. Once I am done, I'm gonna give the signal. I'm gonna give the signal to the register to store the new value. Hopefully, I'm trying my best. But again, in the coming classes, you will understand better when you put all components together to create a computer system. I think that's enough for today. Again, for exams, for anything, guys, I show you the design for 4-bit decoder. I'm expecting that you can do it for 3 bits, for 6 bits. It's the same thing. You just repeat, you add one component here, or you remove. Okay, any questions?